Hello, everybody, and I would also thank the organizer for this nice program, 3-month program I will attend, and for this workshop that has been very intense and enlightening for many interesting discussions and talks we had. So I assume that everyone is a bit tired now because it's quite late and we had a lot of talks. So in my presentation there will be a lot of movies, so I hope you will enjoy them. So the title, I want to explain the title first. A Casimir preserving scheme for long-time simulation of spherical hydrodynamics. So I work in numerics, so I'm not part of the sort of climate scientists. So I spent a lot of time working with the numerics related to the Euler equations. And so I will try to sort of present in this work how numerics can be useful, and in particular how numerics will deal with the conservation quantities. So for 2D Euler equations, Casimirs play a big role. So let's start. The problem of the 2D turbulence started in the 18th century with Euler, which proposed the worldwide famous Euler equations. And so here are the equations. And when I will talk about the equations, but meanwhile I will start the simulation so you will see what these equations cause in this in the evolution. So the equations I'm studying are those of the so-called vorticity form. So the vorticity is the curl of the velocity field, and in order to have a scalar field, we project the curl of the velocity field on the normal of the surface. And in my case, the surface I consider is a two-dimensional sphere. Okay? And we have the normal vector to the surface. Okay, so even if the simulation is projected in the sort of rectangle, these are the sort of standard coordinates, theta and phi. Okay? So latitude and azimuth. And we see that these equations sort of create these strange blobs, vortex blobs. And this is a very interesting feature in 2D turbulence that has been observed since a long time ago. So here in the equation, omega will be the vorticity, and psi is the so-called stream function, which solve the Poisson equation in the second line. And I will consider mainly the case of non-rotating sphere. So omega, which is the rotation of the sphere, will be mostly set to 0. But in the end of my talk, I will show also an example of simulation where the sphere is rotating as well. So here you can see distinguishedly 4 different blobs. And what is the main issue, especially when you deal with numerics of the Euler equations? The main issues are, of course, the conserved quantities, and this encodes most of the geometry of the system, which is a Poisson system. So the main conserved quantities are energy, which is in the first line, the inner product, the L2 inner product between the stream function and the vorticity. Then the momentum, which are 3 components when the sphere is non-rotating, so are the projection of the vorticity on x, y, and z, whereas it's only 1 component when the sphere is rotating, the one referred to the direction of the rotation. And then an infinite number of conserved quantities, which are the Casimir functions, that can be seen as a linear combination of the momenta of the vorticity. So when k is equal to 2, the Casimir is called entropy, and that's one of the main sort of agent in the 2D turbulence. So a bit of history on 2D turbulence and the issues that, the questions that arise in the 2D turbulence. So Onsager in 1949 claimed that, well, we can explain this clustering of vorticity into the ideal hydrodynamics using an ergodic hypothesis for the point vortex model. And this would imply that the formation of the large vortices we have seen. So for those that you are not familiar with them, point vortex model are special solution of the 2D Euler equations that are linear combination, finite linear combination of Dirac delta. And these are solution of the 2D Euler equations. So are singular poles that move around on your surface. And then in 1977, a major discovery of Krajina and other authors that I don't mention here was that for 2D turbulence, we have this phenomenon which is called inverse energy cascade. So the inverse energy cascade has been also known for 3D turbulence from 1941 by Kolmogorov. And Krajina showed that in 2D we have the same phenomenon. And we have that the energy spectrum takes this sort of profile where we have that the slope -5/3 represents the fact that energy at lower scales feeds into smaller scales. Larger scales, sorry. So we have that the energy accumulates in larger scales, and this accumulation of energy in large scales is the cause or the physical principle that explains somehow the clustering of vorticity in large blobs. Okay, and this sort of profile has had experimental and sort of theoretical justifications during the years. In particular, in 1991 and around that period, 92, 93, Miller, Robert, and Sommeria created the so-called MRS theory, which is statistical mechanics theory, which says that maximizing entropy while preserving first integrals, we will reach a steady state, a final steady state for the vorticity. So if you remember, we can write simply the Euler equation using the Poisson brackets on the sphere. So if we have a functional dependence between the stream function psi and omega, then this bracket vanishes, and therefore we reach a steady state. So this is what the MRS theory predicts. In 2013, we have that Herbert, on the two-sphere, specified the MRS theory and found that the final steady state would correspond of 4 large blobs. So according to Herbert, we should have, as a final steady state, 4 large blobs on the sphere. Okay? And this is interesting. If you remember the first movie I showed you, we also noticed 4 large blobs. Okay? So we are getting there. However, in 2014, a very long and detailed numerical simulation of Dirichlet-Kiel and Marston sort of disproved the finding of MRS theory and Herbert, because they saw that, well, yes, we get 4 large blobs, but they are not in steady state. They actually are totally unsteady, and they move accordingly to the point vortex dynamics. So they move as if you had 4 delta poles that move around the sphere. Okay? However, the numerical scheme of Dirichlet-Kiel and Marston had a big bias. So they, in order to get stability in their numerical scheme, they added a hyperviscosity term, and the hyperviscosity doesn't preserve the Casimir. So there is not a direct link between MRS theory and this numerical simulation. So now there are two main questions that arise. Do we need a new theory to explain the unsteadiness of the statistical state of the 2D turbulence? Or we need a new numerical scheme which does preserve the structure, so Casimir, energy, and momentum, to directly compare the MRS theory with numerics. So our work would like, maybe it's too much to respond to both questions. So me and my supervisor, Professor Klaus Modin, in this paper that has to appear in the Journal of Fluid Mechanics, gave the explanation that should tell us why we get unsteady state in the statistical state of the 2D turbulence. And the reason is based on first 2 assumptions. So the first assumption is that the vortex blobs in the hand are separate enough that they move accordingly to the point vortex dynamics. And this is explained in the book of Marchiora and Pulvirenti from the 90s. And then we assume that the inverse energy cascade predicted by Kreiknan occurs. So if these two assumptions hold, then the mechanism is the following. So we start from an initial vorticity, and we have that the mixing of vorticity continues until the vorticity, thanks to the inverse energy cascade, accumulate to large scales and create a certain number of blobs. So when does the mixing stop? The mixing stops when we reach a number of blobs that correspond to an integrable state of point vortices. Okay? So, and what do we know? Well, the point vortex dynamics can be described by the following ODE. Maybe you're familiar already, but I just write here for completeness. Okay? So this is an ODE, and a lot of properties of this ODE are known. For example, it's known that 3-point vortices are always integrable. Okay? So we expect always to get at least 3 blobs. However, if the momentum of the point vortices, which is the sum, the weighted sum of the position of the vortices, if this quantity is equal to 0, then 4 point vortices gives an integrable state. Okay, and if you remember, in the first movie I showed you, we had 4 blobs, and exactly in that case, the momentum was 0. Okay, so this is the physical principle we derived, and the numerical scheme we used to prove this, or to give an evidence of this physical principle, used the geometric quantization discretization in space that has been developed by Zeitlin here at ENS. And also the geometric quantization has been studied by Isabel Gallagher, who proved that the solutions to this model converge to the exact solutions. Strong solutions converge to strong solutions. And then in discretization time is the algorithm we developed, me and my supervisor, which is called the isospectral symplectic Runge-Kutta method. It's just pure numerical result. But when applied to the model proposed by Zeitlin, we have that the entropy and the momentum are exactly conserved as first integrals, and the energy and the high-order Casimirs are conserved, at least for small n. So n is the number of Casimirs. So we have as a Casimir Cn, which is the n moment of the vorticity. So if the discretization level is capital N, for n smaller than n over 2, we have that the conservation of the high-order Casimirs is quadratic. Okay? So it's a conservative scheme. And in fact, so I want to show what the results look like. So here we start from, we had several different random initial conditions. In the paper we have 16. Here I show you 4. They all look the same pretty much. They are all different, of course, but they are all randomly L2 distributed initial conditions. And one cannot guess much from these pictures. So this is the initial vorticity. But when I make them run, you will see the statistical state emerging soon. Okay, so, well, in the corner on the top left, we find 2 or 3 large blobs. One is very small, and I will explain you later why. On the top right, we see 4 different blobs. On the bottom left, we see 3. So it's one of the case we predicted. Also in the lowest one, the bottom right, we see 3 different blobs. So our theory seems to predict successfully the outcomes. And we also have a measure to tell when we expect 2, 3, or 4 different blobs. Okay, so if you remember when I told you that when the momentum of point vortices is 0, we get 4 blobs, then we consider the ratio between the momentum and the square root of entropy. R is the radius of the sphere to make it the parameter adimensional. So when the parameter is very small, we are perturbing an integrable state of 4 point vortices. So we end up with 4 blobs. Okay? When the momentum increases with respect to entropy, then we leave the perturbed region of the integrable state, and we get 3 blobs, as we have seen in the simulations. And finally, when the momentum is very large compared to the entropy, the momentum prevails on all the other possible vorticity, and the vorticity looks like that it follows only the rotation, the momentum, okay, the momentum which is sort of made of 2 large vortices. So in reality, we never get 2 real vortices, but we get 2 big vortices and 1 very weak, which is carried by the momentum. And finally, the last slide, to conclude, I told you that we consider the non-rotating case, but what if we consider the rotating case? It's very easy to implement in this spatial discretization. And for example, here I want to show you what happens from this unstable Rossby-Hurwitz wave if we run the simulation. So this is exact solution of the Euler equation, but is unstable. And we have, even if our scheme is conservative, very little numerical drift happens. And you see that now the sphere is rotating, and what appear like the typical zonal bands, okay? So this means that the statistical state we expect for rotating sphere and non-rotating sphere are completely different, and can be understood also in terms of point vortices, because the point vortex equation, it's only for non-rotating spheres. For rotating spheres, one cannot use this model, okay? So this does not play any role in the rotating case. And that's all. Thanks for your attention.
Time for a question. Yeah. Here we go. Yeah.
Thank you. So if you take a biperiodic domain with an aspect ratio of 1, then
So sorry, which one?
if you take a biperiodic, so periodic in x and y,
Okay, yeah.
and you have an aspect ratio of 1, then you would end up with 2 vortices, right?
Yes, that's right.
And so how does it fit with what you said?
Yes. So the theory works like this: on the square, so or in geometry on the torus, if I understood correctly, you want this surface. So on the torus, the theory of integrability of point vortices work differently. So you have 2 point vortices are integrable all the time if you have point vortices on the torus, and you have 3 point vortices are integrable if the circulation is 0. So you get that this sum has to be equal to 0. Then you get 3 point vortices integrable. In fact, you expect all the time to see 2 large blobs on the torus only, because it's almost like impossible to prescribe a 0 circulation on the final blobs. You can prescribe 0 circulation on the total vorticity, but not on the final blobs. Okay, because when the blobs appear, there is a background vorticity. You know, the total sum of the vorticity is equal to 0.
Okay.
Exactly. But the final blobs, you never know if the circulation is 0. And that's why in numerical simulations that I have also, we did also for the torus, but of course the torus is more known, so it was less interesting somehow in this case. You always end up with 2, because in general only the 2 condition is integrable. Whereas for the sphere you have total control, because the momentum is a conserved quantity, so it's a first integral that you can prescribe at the beginning of your simulation. And this is very interesting because it's related on the group of symmetries of your equations. On the sphere you have SO3, on the torus you have R2 as a group of symmetry. And that's why you get this.